You have to adjust in mid. Wow, that sounds hard.
Take two.
It's almost like a miracle anybody hits it.
It is. I mean, 100 mile an hour, that's a pretty fast ball.
Yeah, it's only that big, so how do you see that from that view away?
Well, you know kind of where it's going. Kind of.
What's funny is when people who are doing like the opening pitch get out there and can't throw it 90 feet, you know?
Or even 64 hop special.
I'm sure that's what I would do.
Okay,
You ready for me? Okay.
I'm ready.
All right, I'm going to go ahead and start. What I'm going to do is a very rough cut of what will become a RubyConf talk within a couple weeks. And the subject I'm going to be talking about is machine learning. That used to be machine learning for fun and profit until I saw that there were like 3 other talks at RubyConf called X for fun and profit. So now I've got to come up with something better, and I haven't yet. Machine learning, insert cliche here. I may just keep that, actually. Okay. Done. So, I'm Chris Nelson. I'm with Gaslight. Blah, 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 introductory stuff that I already said for you guys, so I'm not going to do. So, first of all, the subject that I'm talking about is really broad. And what I'm really talking about more specifically than machine learning, which is really general topic, is I'm talking about classification, and we'll go into a little bit of what that is. I'm really going to be spending most of my time in terms of specific algorithms talking about just one, really, maybe 2 by the time I get to RubyConf. And this is all kind of based on a specific experience I had with a specific project that James back there was on with me. So if James wants to jump in and interject at points, that would be totally awesome. But it's really about how to recognize problems that are a good fit, and what classification can and can't do, and some other options that I've come up with that really aren't all that new, but I'll tell you how I actually solved the problem that I was working on. So, the story, and there needs to be more on that slide, of course, but there isn't yet. So, the story is James and I were working on a system for a state government, and what they were doing is giving people a way to find out what programs they might be eligible for as a multi-family property owner. And part of what it did along the way is, based on a questionnaire that they filled out, it would recommend specific upgrades for their properties. And then later on it would tell you, here's some programs that you might qualify for to implement these upgrades. But one of the things that we were doing is figuring out, okay, how do we take the information they've given to us about all these different programs and all these different upgrades that a property owner might or might not want to do to their property based on certain criteria. How do we actually implement that in code? And there's some really good things about the project. They had done some really good work ahead of time before we even got there. They had come up with, they had the rules for how to recommend a specific property upgrade very well thought out, even to the point where they actually had cucumber tables that would describe, what, in a specific case of, okay, the property fits these criteria, is this an upgrade that they should do or not? So they had done a lot of work ahead of time, but there were still a lot of rules to go through and implement. So, we were pretty excited that we had cucumber tables at least. It was a pretty good situation, and so we started in on it. And here's an example of a really simple rule that might be in this system. This is a rule about, should I upgrade the pool pump at this property? And so there are different criteria, and it's very simple. Do they have a pool, first of all? No, if they don't have a pool, well, they probably shouldn't upgrade their pool pump. Next, they do have a pool. Do they already have a really efficient pump? No. Well, I think I might have that switched around backwards, don't I? Oh yeah, no, that's right. If they don't have an efficient pool pump, then recommend an upgrade. If they already have an efficient pump, then don't recommend the upgrade. So it's pretty much like the hello world of rules. Not very hard to implement. They had a nice cucumber scenario with a table of data for us to run it through, and it was just great, and not too bad at all. And it turned into, as you might guess, really simple code. We had a pool pump rule. This is not actual code. This is just sort of made up. But something like this, if the property has a pool and the property does not have an efficient pool pump, I've got to go in and fix that later. Does not have efficient pump. Then that rule would be true. So this was all good, but then we came to a more complicated rule, and this would be about whether to upgrade the heating system for the property. So this falls into, and this is like a really abbreviated version of actually a much, much longer rule. This basically breaks down along what type of heating do they have, and based on that kind of heating, what's the efficiency for that kind of heating type. If they have gas furnace heating, is the efficiency above 0.78, and I forget the specific units there, but it's not really important. If it is, well, then that's fine. Don't recommend an upgrade. If it's under that threshold, yeah, go ahead and do recommend the upgrade. If I don't know what the efficiency of my gas furnace is, well then, is that heating system, was it installed more than 18 years ago? And if so, recommend the upgrade. So it quickly becomes fairly complex, and as you might guess, it becomes somewhat more complex code-wise to implement. So we still had our cukes to tell us whether we were right or not, and we just went through and started implementing this in code. Go ahead.
You want to fix the bug?
Which one?
Heating installed at less than 18 years ago?
And
If it was installed yesterday, it was installed greater than 18 years ago. Is that a timestamp?
probably so. Yeah.
That'll save you time. Same thing with greater than 30 years ago.
Yep.
Which kind of just emphasizes your point that too logic code is hard and it sucks.
Yeah. So basically our approach at the outset was to write this by hand. And this was all pretty good. You know, great. Hey, we have 2 down, only 30-something to go. Oh yeah, and with unit tests. And oh yeah, we were supposed to like try to be done with this by the end of the week. So yeah, we started kind of trying to come up with a better idea here. And fortunately, James had the insight to say, hey, you know these cucumber tables that we have that express these rules? They look a lot like decision trees. And so my first question was, well, what's a decision tree? That's not something that I'd heard of or gone into for quite a while. Decision trees, like I said earlier, they're in the general subject of machine learning classification. And what they do is, given a set of examples, they learn how to classify things. So if we look back at our table from earlier, what they specifically do is they take a table of examples, which is exactly what this looks like, and generally the column at the end they use to, based on these examples, if I give it a new, representative sample, which one doesn't match, and predict the outcome. So what's a decision tree? Really, a decision tree is just a tree of the decision, the possible decision paths that you can go through. So this is like the simplest representation of a decision tree from the original pool pump rule. Do we have a pool? Yes, no. If we get to no, then it's not recommended. If we get to yes, then we go down to the next thing. Do we have a high efficiency pump or not? Is that going the right way? Is my arrow backwards? If we yes. If we have a high efficiency pump, then it's not recommended, so that's going the wrong way as well. Logic is hard.
It's too bad your understudy didn't catch those.
Yeah, well, I didn't. I'm totally lame.
Make time to meet, so
It's too bad we didn't make time to meet is what it really is. Pump in diagram. All right. So for the more interesting decision tree, I was going to actually try to draw out that one that we looked at in the heating system chart. I don't think I'm actually going to do that. Hopefully you does it make sense so far what a decision tree is generally? I kind of don't feel like another larger one would actually help that much. I'll probably do one for RubyConf, but I think I'll skip it for now. But the thing about the decision tree is, for the case of the really simple one, and this is probably where I do need a picture of a more complicated one, there aren't very many choices. There's only two choices of where you would actually put the root of that tree. And only one, it really only makes sense the way it is up here. But if you had a larger tree, the question is, which criteria do you put at the root of the tree? Which one do you start with to go down into the branches of your decision paths? And that's really what the decision tree algorithms are about. How do I actually figure out where to start my tree so I start branching down and have a reasonably efficient tree? It turns out picking the most efficient tree you possibly can is like a NP complete or something problem. It's like very hard to solve, and it's like traveling salesman. You just, you run out of computing resources trying to solve it. But there are some algorithms to take a reasonable guess at it, and that's what we're going to talk about here. So imagine in your mind a more interesting decision tree, and that's the question we're talking about here, is which do we pick as far as where to start our tree? So I'm going to now try to explain the concept of entropy. So entropy is, and I guess I should probably add another slide here. One of the more common or well-known, I guess, algorithms for how to build these things is called ID3. And it uses a measure called entropy to pick where to root the tree. And what entropy actually means is for that, if we went back to that first table, the entropy is really about, how many possibilities are there for that path for the upgrade recommended here, and how disjointed is the set of data? I don't think I'm explaining that very well. You want to take a crack, James?
So, given the set, it measures the amount of branches, I guess, would be the best way to say it.
How sparse or how full your table is?
Yes.
So
back to the mathematical.
So it's really about how many bits do I need to try to represent the possible outcomes. And so in this case, and maybe I need to pick a better case to actually look at this with, there are going to be two possible outcomes, and it would be going through all the possible outcomes. That's the one to see there, is all the possible outcomes. And then that's in this set, for each outcome, what's the probability of that outcome times the log base 2 of that probability. So it's adding all those together. And that's kind of measuring how variable that set of data is, I guess is the best way to put it.
So S represents the entire set of data? S represents-
The entropy of this set, yeah. What, was somebody about to say something? Okay. So the other concept that I'm going to try to explain is information gain. And I think I can explain this in words better than I can go through the math, although I need to get a better handle on that too. But information gain is about the difference in entropy if I actually subdivide on one of the criteria. So for instance, if I look at each of these columns, if I look at each of these columns as something to split by, how does choosing a value of this column affect the entropy? How likely is one of these columns to affect which outcome? So for instance, if every time I picked one of these values, it corresponded exactly to all yeses or all nos, that would be like a very high gain in terms of entropy, because the entropy for, all the, let's see, I probably need a better example, but let's imagine for above 0.78, it was all no's, and below it was all yeses. That would be like the highest gain you could have, because essentially the entropy of each of these paths goes to like nothing. They're all the same. There's no variability anymore. So the gain actually calculates that mathematically, and that's how ID3 actually figures out where to root the tree, and it does that recursively. So it'll figure out, okay, what column has the greatest effect on the outcome, use that as the root of the tree, and then when I go down, figure out, okay, what column has the next greatest outcome, and so on and so forth, and that's how it builds up the tree reasonably efficiently. So does that make any sense? 0 sense? Questions? I feel like this is like the core of like, how do I make this a good presentation, is like, can I explain this better? So if anybody has any feedback now or later, that's awesome.
Picking the root is about coming up with the most efficient tree to use during execution?
Yeah.
Okay. It's not that any particular root would be any more correct or incorrect than any of the other ones. It's just how fast can I derive an answer based on picking this particular thing as my root, right?
Yeah, I think that's true, and I probably need to do a little bit more studying, because maybe in some cases there are trees that, like, if you pick the wrong root, it would just not make any sense at all. But
If you were looking at binary trees and Huffman coding, is it sort of analogous, where you're trying to find what's the best way to encode the yes/no choices?
Yes.
Yes,
That's
I
exactly
mean,
right.
most people will probably have heard of Huffman coding.
that's a good example.
Yeah. So
okay, but I'm gonna have to brush up on it. I'm sorry.
So Wikipedia has like a three-point like explanation ID3.
Yeah.
You take all the unused attributes and count their entropy concerning test samples. You choose the attribute which entropy is minimum, or equivalently information gain is maximum, and then you make a node containing that attribute, and basically it tags that node tree with pluses or minuses. Adds up if the number or predicting value is empty, then return the single node tree root with the label equal to the common value of the target attribute in the examples.
So that was the simplest?
I don't know if
That's the simple explanation.
So it's
That's why, it's like,
summarize.
it's kind of a hard concept to.
it sounds to me almost like a power score in statistics, like whether or not something is like going to be highly correlated to a successful outcome or something defines its power score. So you can have multiple things that are predictive.
Yeah. Something like this. I think I probably need to go into, is to find a way to make a really simple way to actually show these calculations.
If you copy that table underneath this equation,
Yes.
and then start drawing like color-coded lines to show where is it strong and where is it weak.
Yeah, that's a really good idea. Tables.
And then you could also take your blown-up view again and do the same thing and say, look, this is how this tree looks. We'll
Underneath
do the entire process.
gain and entropy. We're gangbanging out my RubyConf presentation. This is awesome.
We're not supposed to use that phrase.
Oh, I'm sorry.
We're fishbowl
Fish bowling. Yes.
crowdsourcing.
Crowdsourcing. Crowdsourcing. Swarm presenting. Yes. Groupthink. No, that's bad. Okay, so let's talk about AI for R. AI for R is a gem which implements a bunch of different AI algorithms in Ruby. And one of the things that it implements, conveniently enough, is the ID3 decision tree algorithm. And so there's a few other implementations out there, but as I poked around, this one seemed to be the strongest and easiest to use and best. So I'll have a few slides in here at RubyConf time, but for now, I think their documentation describes it as well as I can. So basically, if you take a table kind of like the ones that we were looking at before, and basically these would be the column headings at the top of one of my tables, and feed it a set of examples like this, it will be able to actually build up the rules in code based on that decision tree. So it's literally taking in the table of examples and spitting out that code that I was writing by hand. Exactly. Kinda. And we'll get to the kinda in a minute. But, so, I mean, this was like, wow, this is like magic, right? So, the first thing that I started looking at is, okay, taking those tables that the customer had already provided to me, they were in Cucumber tables. Well, those are pretty easy to parse. There's actually some code that you can pull out of Cucumber to parse them. Feeding them through the ID3 algorithm and actually taking this code and evaluating it within the context of that domain object that represented the property. So for some of the rules that worked really well and actually satisfied the specs, and actually it was the first few I tried. So I was really excited, and then I unfortunately found some cases that it didn't work out, and I'd like to kind of talk about those now.
So you're feeding it examples or rules? The table is more like feeding.
Yeah, that's a really good point.
Can you bump the font on that?
Yeah, good call.
Yeah, but if you see the data items there, those are more example driven because you have things like New York and Chicago repeated like bigger than 30.
Mm-hmm.
And you got those repeated all over.
Yeah, and you can see when you say get rules there. Yeah, that's exactly the same branching conditional logic.
If you already have the rules, that's kind of like the best example set you could have.
Well, sure.
Yes.
They're
Deterministic.
yeah, and you've already done all you've done the learning part already. It's when you start with the raw data, like
Oops.
just a bunch of data points, trying to figure out what the rules really are in the first place.
So in theory, this could be a very large database of a bunch of stuff that you just had no idea what the rules actually were,
Right.
Yep.
but you assumed it was correct.
Here's our last 10 years worth. We assume we did them correctly.
Right.
So yeah, this was kind of like magic. So sometimes if it sounds too good to be true, it turns out that it is. And here are some of the things that actually you come up with when you actually use the ID3 algorithm. So we talked about entropy earlier, which is basically the whole concept of entropy and information gain is if I pick a certain value for one of the columns, how accurately does it predict the outcome? How many, if I pick this value, how many different outcomes are there? And the fewer the better. The more, that's basically saying how accurately it predicts the outcome. So entropy bias, what that means is this algorithm works pretty well for sets of data, much like the ones that we were looking at. Rather than go back and forth all over the place. It works really well for things that have a discrete set of values. So like for has pool pump, that was great because that's yes or no. And you noticed, I think in one of the rules where we talked about installed, and I had values in the table like less than 18 years, more than 18 years. That's, well, and probably one of them would have to go this way so that it actually breaks down into a finite set. That's pretty well, that works pretty well because we have two possibilities to choose from. Where it starts to break down is, what if those were actual dates? Can anybody guess right away what that's going to do to our algorithm that picks based on entropy and information gain? So if I pick one of these, anytime I run across one of these, what are the chances that the entropy is going to be like, it's always going to predict the outcome? It's really, really high because there's almost always going to be like one entry for this and it's going to correspond to one outcome. So basically it's always going to pick date as the root, even though in actuality, date is a terrible, terrible predictor of the outcome of, what the actual value should be over here. Does that make sense?
Because you were working with the actual rule set and they were all weighted equally, as opposed to a data set where you have some portion of them using that rule.
Yeah, yeah. So it worked okay in my case, and I didn't actually run into entropy bias. But if you're using this algorithm and you have a column with a bunch of different possibilities, it may not be a good choice for you because it's always going to pick that column. It's always going to pick that attribute to root the tree from. And that ends up being like not a very good predictor of the outcome and not a very good thing to pick. So it's again like it's important to understand exactly how this thing works. At first it appeared to be like a really useful magical black box, but when you actually dig in and understand it, then you see, okay, where are the cases where this is actually a really good fit, and where are the cases where it's a really bad fit.
I guess one question, would you then be advocating for manipulating that data somehow to turn those into greater than or less than, or sort of the date ranges?
That would certainly be a way to do it. And I don't know if I have enough time and decide to go into it. So ID3, I really need to put this in here. Quinlan is the guy's name who came up with the ID3 algorithm, Ross Quinlan. He actually has an improvement, which I have not seen a Ruby implementation of, called C4.5. It's another algorithm that uses entropy, but I guess from what it says, and I haven't seen this implemented in code and tried it out, but it will take an attribute like this with a range and actually figure out, where's the significant point. It will figure out from looking at the data, okay, well, I need to divide these into under 18 years and greater than 18 years and actually handle that kind of thing for you. in the data that I was looking at and working with, they'd already done that work for me, essentially. But there's an improvement to the ID3 algorithm that can do that as well. C4.5. Unfortunately, I did not see an implementation of that in AI4R. I was really hoping I would. Yeah. Yeah. C4.5. And then there's another one after that called C5.0, which he commercialized, and supposedly it's like super efficient and awesome, and I don't know any more about it than that. So what I actually, and actually there's another problem in my set of data that made, and this is actually the problem that stopped me from going forward with ID3. If you look at my set of data, Joe raised a really good question, is my data examples or are they rules? And that's a really good question, because in my case, they're rules. And what the next problem that I ran into is, what does blank mean? And in my case, blank means I don't care. And that's different than I don't know. And it's also, it doesn't work well with this ID3 algorithm. It didn't really work out. Essentially, what it would have to mean in the context of ID3 is basically like my table would have to be multiplied by, all the possibilities for this value and a no answer and everything else the same. That's essentially what I don't know means in the context of my table of data. Is basically I was missing a bunch of examples. And in order to make ID3 work, I would have had to figure this out and multiply my example data by all these blank values. And that just was obviously a silly thing to do. So that's what actually stopped me in my tracks as far as actually using ID3 to write my code for me. However, what I realized is the problem that ID3 is actually trying to solve, which is which of these to use as the root node of the tree, is actually a problem that I didn't have. Because I know that anytime I go across here and I find a match, and it's all I don't know at this point, if I find a match on these two, I don't care about these. If I find a match on everything in here that I care about, that's the outcome that I pick. I just have to go down this list, and the first matching rule, bang, that's the outcome. So what it turned out for me is like the work that I had to do already to make ID3 a possibility was basically come up with domain methods for all the columns over here so that ID3 would spit out code that actually worked. That effort that I put in to actually, massage my domain, massage my problem space, I'm not sure how to word that. That was actually all good. That was completely valuable. It's just that the part where ID3 spit out the rules, I could have a much simpler implementation of that. And so what I ended up doing was writing a much simpler thing, which I called a decision table. And I expressed that as a gem that basically just does that. It basically goes through the table straight down and says, okay, for each one of these guys, does my domain match on everything that I care about? Okay, well, if so, I'm done. I pick the outcome, I'm done. If not, I go on to the next one. So it's like really simple brute force, not terribly elegant, but it worked to actually solve the problem it had. And we were able to feed it all these cucumber tables, not write the code ourselves. And what we did was we'd actually written the first several rules by hand, had unit tests and cucumbers around them. So we were able to swap out my implementation that worked by reading in these rules and run the unit tests and cucumbers against them to verify that my tool was actually doing the right thing. So decision table, like I said, is a Ruby gem that's out there in the wild at this point. And it's not really a decision tree. It's basically just a way to interpret rules expressed to you in a tabular format. And it ended up being just the right thing to suck in these massive amounts of rules and execute them. And this is an example of how it might be used. This is a rule about attic insulations, I think. Is it well insulated already? Okay. If true, well then I don't care if the attic's accessible. You can't do it, so don't recommend it. And then if it isn't well insulated, but the attic's accessible, then you should do it. But if the attic's not accessible, then you shouldn't. So basically it takes a two-dimensional array like this. You parse your table into a two-dimensional array. And then it produces a rule set. And it expects a rule set if you give it a domain object that has these guys as methods, has your column headings as methods, it will return the first applicable rule. It'll basically return the first outcome where there's a match.
So it kind of turns out like the last column in the table is like the answer key, and every other column is like scenarios to match against that answer key. Right? Each row is the scenario that matches that key.
The other thing that I ended up doing with it later, in another case where I realized that I had something similar, or I wanted the customer to be able to express what they wanted to do to me in a way that didn't involve me writing code, but they really didn't have a set of rules. They only had like a single row, basically. I implemented something like this where basically it will bring out the outcome of, if this user doesn't drink coffee, does write Ruby, has 2 children, then this rule set matches. So basically it's a rule set with a single rule. I ended up having that be a useful in a system where I had packages of products that they were to offer to different types of customers, and each packet had a rule specification somewhat like this, where that package would be offered to the customer if he satisfied the rule. So essentially, it really is basically a kind of a little DSL at that point for the customer to be able to write rules in. That's another case where I ended up taking the same code and actually using it in production.
Played around with this Jim for like a quiz site type thing, and it turns out it does most of the heavy lifting for you. So if you ever filled out like one of those silly quizzes like, what's your favorite color, who's your favorite My Little Pony, and at the end it tells you what He-Man character you are, like this Jim basically will do all that logic for you. You just have to spell it out in Cucumber, basically.
Yeah. So I may or may not have had more slides to go through. So yeah, I think that's about the end of what I have so far. So I guess some of the important things that I learned during this whole thing is it's really important to understand the trade-offs of whatever algorithm you're using. It's what at first appeared to be kind of something magical was magical within a set of certain circumstances, and different. With a lot of the AI algorithms, they're good at different things, and understanding what a particular algorithm is good at is really important in deciding which one to use. And then the other thing I learned was, sometimes you don't need something as complicated as you might think, and brute force, until it's not good enough, it is good enough. So that's what I got. Questions?
Well, not necessarily a question, but it seems like it'd be good to add in some kind of scenarios where the
AI for R.
yeah,
Yeah.
that gem would be useful.
Mm-hmm.
Coming up with scenarios because you're showing how to use
Yeah.
it, kind of. So
Yeah.
it seems like it'd be
So
good to get
where it would
going.
be really, yeah, and I think it would be useful where you do have a large set of examples that you know, can make predictions based on, but don't necessarily know what the rules are yet. That's really where it's more useful. And of course, beware of the entropy bias if you're using something with a bunch of different possible values for one of those columns. But
You
yeah,
mentioned
you're right.
the traveling salesman problem, and that's one that AI for R actually could potentially help you with, because one of the other kind of types of algorithms it has is Ruby classes for doing genetic programming, right?
Yeah. And I do have a little bit of space left in this talk, and that's one of the things I was thinking about doing, is kind of going into what are the other algorithms in AI for R and what are they good at. I don't know if I have time in 45 minutes to get into too many of them, but I could cover a few.
It seems like it'd be really good for like multivariate conversion tracking kind of stuff, to come up with like what the best arrangement for different things on the website would be, something like that.
So,
But I don't know exactly how you implement it in a slide.
yeah. Well, that's all I got.
Nice job.
I should turn off my thing so it doesn't project.
Can I turn off my thing there?
Yeah, I'll take it.
Madagascar 3 is hilarious. Easily the best one yet.
Really?
It says worse as they go.
That's what it says.
Oh. Guess I should actually read before opening.
You can't argue with the marketing.
Easily the best one yet. We set the bar really low at the previous school.
Easily the best one yet.
Easily the best one yet.
So I will mention that Super Chris was nice enough to come and speak. Jim actually was going to speak tonight and wasn't able to make it because of a scheduling conflict. So
But we'll get them another time. Did he do it for the other Ruby Brigade?
yes, he did. Yeah.
Get him to revise his talk for this.
Yeah.
What was he going to talk about?
I actually don't know what the talk was on. This was the Oklahoma City user group, and I think if you go to their site, you might be able to see it.
You gotta look at the Ruby site. He's outlining